Good day, everyone. I am Winardi from Universitas Multimedia Nusantara, Indonesia. Today, I will present my research titled Classification of Deepfakes in Static Facial Images using Deep Learning Ensemble with Weighted Averaging Approach. This work was conducted as part of my undergraduate thesis, supervised by Mr. Mulyono Wijaya. The focus of the study is improving deepfake image detection using multiple deep learning models combined into one ensemble system. To start the presentation, I will begin by discussing the background and motivation behind the deepfake threat. So we know that artificial intelligence and computer vision have enabled impressive digital content creation, but it also led to the rise of deepfakes, a synthetic media generated by GANs. Techniques like style gun can create photorealistic faces that are almost impossible to distinguish from real ones. While it is beneficial in creative fields, deepfakes have also been misused in misinformation, identity theft, and non-consensual media. It threatens social trust and information integrity. So this motivates the need for reliable deepfake detection systems that can ensure authenticity and security in digital media. Okay, for the problem statement and research objectives. So when I researched on some papers, I found that the current deepfake detectors mainly use single deep learning models, such as CNNs or ExceptionNet and other deep learning models. Although they perform well on specific datasets, I find that they often fail to generalize when tested on fakes generated by other methods. This issue is called by domain overfitting, which is a major limitation. Therefore, our objective is to develop an ensemble deep learning model that combines multiple architectures using weighted averaging. We evaluate its accuracy and robustness, and then we analyze its generalization capability on external datasets. So our research methodology pipeline overview follows a four-stage pipeline. The first, we have data preparation, where we acquire, we pre-process, and split the dataset. Next, we follow by model development, where we train four architectures and combine them into an ensemble. The third one, for the comparative evaluation, we test both individual models and the ensemble model. And finally, for the analysis and interpretation part, we try to understand the performance of each models and the generalization behavior behind it. So this structured process ensures a consistent and reproducible workflow from start to finish. Okay, now let's dive deep into the research. First, we are going to discuss about the datasets and pre-process strategy. So we used the 140,000 real and fake faces dataset from Kaggle. It contains 70,000 real and 70,000 fake facial images, which is generated using StyleGAN. Each image is consistently 256 times 256 pixels. So we made sure that every data that is consistent in quality. Then we divide the data set into 100,000 for training, 20,000 for validation, and the rest 20,000 is for testing. The preprocessed part also involves normalizing pixel values between 0 and 1, and then applying minimal augmentation, which is random horizontal flipping, which is we did only minimal augmentations in order to preserve subtle forensic artifacts important for the defect detection. Okay, now let's dive more into the component of the model architectures. Uh, so the ensemble combines four distinct deep learning models. First, we have custom CNN, which is designed specifically for deepfake detection using four convolutional blocks that extract hierarchical features. The rest three models is pre-trained models, which is ResNet 50, a residual network that enables deep feature learning through skip connections. We also have exception model, which separates spatial and channel-wise processing in order to capture subtle inconsistency between pixels. Then we have efficient net B4, which scales depth and width efficiently for multi-scale analysis. uh, so each architecture in the ensemble model provides a different perspective on detecting synthetic artifacts. We hope that it will help in improving overall diversity in the ensemble model. Okay, now let's go for the ensemble method. So we chose weighted averaging as the ensemble method. So each model's prediction is combined using the weights proportional to its validation accuracy. So this ensures that models performing better contribute more to the final decision. The ensemble prediction is computed as the sum of each model's output multiplied by its corresponding weight. So compared to other complex stacking or boosting method, um, we found that this method is simpler, faster, and less prone to overfitting, making this a more ideal for deployment and interpretability. For the core results of the ensemble performance on testset, so all models achieve a decently strong performance. We have exception on 99.2%, custom CNN on 98.81%, EfficientNet on 96.35%, and ResNet on 90.10%. But the ensemble outperformed them all, reaching of 99.64% of accuracy. It also reduced false negatives by 78% and false positives by 46.5% compared to exception model. These results confirm that combining diverse architectures effectively mitigates model-specific weakness and help improve detection reliability within the same data domain. To test the generalization, we evaluate the ensemble on an entirely different dataset. So not a split dataset, but an entirely different dataset, which is the fake phase. Here, the performance dropped to around 50% accuracy, equivalent to random guessing. So this shows a severe domain overfitting problem, meaning that the models learn style-gun-specific artifacts instead of universal deepfake features. It emphasized that the gap between laboratory accuracy and real-world performance and highlights the importance of multi-domain training and cross-dataset evaluation for future research. So to conclude, this study introduced a weighted ensemble approach combining four deep learning models for deepfake detection in static facial images. The ensemble achieved 99.64% accuracy, outperforming all individual models and significantly reducing error rates. However, cross-dataset results reveal a major limitation. The current detectors lack generalization to unseen fake types, where we know that future work will have to focus on multi-dataset and domain adaptive training, trying integrating frequency domain features and maybe using frameworks like deepfake batch for standardized evaluations. So we hope that this research contributes both a strong baseline and an honest discussion of the challenges that remain in achieving reliable real-world deepfake detection. That will be all. Thank you for your attention.